Okay, so the next step is quantization, okay, where you will reduce the number of bits per sample. So this quantization is done after you do the transformation using DCT. So what you will do, you will reduce this number of bit, okay, to be as one of the to reduce the size of DC and AC. So you will have the DCT and also the quantization table. So means that, as you can see here, so the coefficient value is high. So what you will do, you will reduce, okay, by divide, okay, with the quantization. So if you divide, so the number here will be smaller. So that's how the quantization will be done, where you will reduce, instead of maximum 120, now the maximum is only 12. So means that you will use less number of bit compared to the original. Okay, so you will divide 120 by 10, 60 by 10, and at the end you will get this. Okay, so you will round it. So more numbers of zero, sequence number of zero will be obtained, okay, after you do the quantization. So consider a quantization threshold value of 16. For example, here you will calculate the difference. Okay, so this is threshold value. So you will have consider a quantization threshold value of 16. So first you derive the resulting quantization error for each of the following DCT. Okay, so you will get this. For example, here you have this DCT, then you quantize. Okay, means the threshold is 16, means each of these will be divided by 16. So you will get these numbers. Okay, 72 you divide by 16, so you will get 4. Okay, so you have to round all this to get this one. Okay, if it is in negative, so you round it negative, it will become -4 or -3. So then after you round, you have to dequantize. Okay, so for this reason, for this dequantize, what you will do is to get the error. Okay, error means you will see, okay, you target to have less error. So when you dequantize, you have to multiply back with the 16, then you will get this. So error is by get the difference between the quantized and the coefficient original. So you will get this. So max error or threshold is equal to 8 divided by 16. So you will get the max error is within 50% of the threshold. Okay. This is just to show you, okay, once you do the quantization, you have to calculate the error. Okay. Next step is entropy. Entropy will divide into 2. Vectoring. Okay, you will do the vectoring, means that you will sort your image of 2D into a 1D. So in vectoring, you will do the entropy encoding step, okay, where you will do the vectoring, okay, you will do the differential encoding, okay, and you will do the run length encoding for the AC. So as been mentioned, if you divide, once you get after transformation, you will have DC, okay, and also AC and DC. So for DC, you will apply differential coding. For AC, you will do run length encoding. So output of this, then you do the Huffman. So let's go on to the vectoring. First you have to do, so you will scan zigzag. Okay, it is not from top to bottom, left to right. So you will do a zigzag scanning, so that the correlation is much more compared to top to bottom. Okay, so you will get this linear vector. Okay, you will get the DC. So this is DC, the rest will be the AC. Okay, then you will sort. So let's look for this example. Okay, then you will do the entropy. So this one is only considered as one. Okay, one plane. Okay, one block. If you have an image which divided into block, all the DC will be in one. Okay, you will do the DC and also AC. AC is for each. Okay, so what I mean is, originally you will have a big image, okay, and then you will divide into block. So you will have DC here, DC here, DC here, until the end. So this DC will be in one. So that's why you will do the differential coding. So all the DC will be combined into one, and you will apply the differential coding. So for each block, you already have the AC. So you have the AC, sequence of AC here, sequence of AC. So each of the AC in each block, you will apply the run length encoding. So in DC encoding, DC coefficient, you will apply differential encoding. So a DC coefficient is a measure of average color, luminance, and also chrominance associated with the corresponding 8 times 8. So that's why DC is very important. Okay, so once you do the decoding or you inverse the process, so it will refer to the DC coefficient, so that all the color, the luminance and chrominance will not lose much. Okay, say the DC of a sequence of DC is this. Okay, so this is come from different block. So each block will have their own DC. So you combine, okay, all the DC to be a sequence of DC coefficient. So this DC coefficient will generate the corresponding differences value. Okay, 12. Okay, so 12 will be the initial, which to be referred after. Okay, so you get the difference between these two. 12 and 13, you will get 1. 13 and 11, you will have -2. Okay, the difference between the adjacent. Okay, 11 minus 13 is -2. 13 minus 12 is 1. Okay, 11 minus 11 is 0, 10 minus 11 is negative 1. So that's how you get the difference between the DC coefficient. So then only the difference in magnitude of DC coefficient in a quantized block relative to the value in the preceding block is encoded, okay, in the form of SSS value. So from these different values, you will encode it in using SS and value, where SS indicate the number of bits needed to encode the value. Okay, so you will refer to this table. So when you want to encode, you will refer to the different value. Okay, for example here you will, so this is the different, okay, the different value. If the difference is 0, then the number of coefficient is 1, okay, and the number of bit to represent this 0 is 0, okay, and the encoded is 0. If either 1 or negative 1, if the difference is negative 1 or 1, you will need 1 bit. Okay, so the number of coefficient is 2. This only one coefficient. So this one can be 2. So means that you will need 1 bit. Okay, 2 power of 1 is 2. So that's why you need 1 bit. If it is negative 2, 3 and negative 3, so number of coefficient is 4. Okay, so you will need 2 bits to represent this sequence. Okay, so how to get the negative? Okay, by getting the positive first. So you transform into binary. 2 is 1, 0. So negative 2 is the complement of 2, which is 1 become 0, 0 become 1. So this is how you generate the table, so that when you encode the DC, you are referring to this SS and also the value. Okay, so next, let's say this is the DC coefficient, the same example as before. So first you have to get the difference, okay, between this. So first is 12, 13 minus 12 is 1, 11 minus 13 is negative 2, 0 and negative 1. So then you want to encode this. So you have to get the SS and also the value. So for this 12, okay, you will need 4 bits. Okay, so the binary of 12 is 1100. Next is 1. Okay, so that's why you get this one, 1100 SS. Okay, and also the value. So the final encoded is 11100, 1, 0, 1 and 0. Okay, so this is the value. 12, 1, negative 2, 0 and negative 1. Then you transform into SS. How many bits we need? So 12 you will need 4, 1 you need 1, negative 2 you need 2. So once you get the SS, then you will transform into a binary. Okay, 1 is negative 1 is 0. So this is a DPCM coding. So that's how you encode the DC.